close to 8 people or something.
Great.
So once, either one or two a week. Um, so yeah, we've been pretty busy with that. Um,
Fantastic.
the other thing is that we distribute
Like to go ahead and introduce them,
Sure.
and we get rolling. Thank you.
Great. Today we have welcome everybody. Actually, today we have a special guest from JPL who's been working on robotics and also has been a researcher as well. So he can really give us a lot of information about robotics and all his projects that he has worked on. Uh, the way I met him was through a friend from Australia, and sure enough, he's also an Aussie. We Australians would call them Aussies, I guess. And so I sat down with him and over lunch, and we had a meeting, and we talked about our program here at Oxford Academy and what we've been doing. We've been participating for at least 9 years, I guess, close to 9 years. And each year we're getting better and better. We really hit uh, our top of our game last year when um, we were seated number one in one of the regionals and came in second place and gave us an invitation to the world champions at Houston.
Wow.
So we're pretty proud of that. Our team is getting better and better. I'm happy to announce Dr. Benjamin Morrell, who's going to give a talk and um, enlighten us with robotics. So, welcome.
Thank you. Thank you. And a pleasure to be a chance to meet with you guys and to present. And I'll put up some slides shortly and go through those. But please kind of compile your questions, and because I think it's also great for me to spend my time answering any things that you guys might be curious about. Um, so I'll jump onto the slides now. All right. So first off, start with a bit of introduction to kind of JPL and NASA. Now, you guys might know a bit of this already. I know you've had some presenters already from NASA, but you've seen robots, or you may know of robots such as the Mars rovers, such as Spirit or Opportunity. These are rovers exploring other worlds. But then there's also spacecraft that orbit around other planets, about other moons, that are essentially robots, robotic explorers that are going around space, going around our solar system, looking to find different things. And for both of these cases, it's all science is the goal that they're looking for. And so there's a robotic platforms, a rover, a satellite, and even things going beyond our solar system. This is the Voyager spacecraft. And JPL and this NASA lab in Los Angeles, their job is to build these robotic explorers to go out and into the solar system. And this is a bit of a family history of all the different missions from JPL. And by missions, what I mean is a mission is a one single robotic explorer going out to do something. So the Mars rover is a mission. The Cassini going around Saturn is a mission. Each of these lines are different launch dates to different parts of the solar system. You've got all the different planets. You can see a lot of missions to monitor things on Earth, going to the sun, beyond the solar system, some astronomy, and comets and asteroids. And so there's a large number of these robotic missions that JPL has sent out to go and explore. And what I wanted to do in the presentation today is to go through what does a typical mission look like for creating these robotic explorers, and try and link it to see how the elements that you guys are going through for FIRST Robotics, how that's actually very similar to what engineers and scientists go through for designing things like the Mars rover. And so, first of all, just a little bit of a background on myself. I went to university here. It's not Hogwarts, it's actually the University of Sydney in Australia. And there I did aerospace engineering. So that's, it's kind of a bit of mechanical engineering, electrical engineering, but looking at aircraft and spacecraft. And I got really interested in how we control aircraft, and that eventually came into how do we control robots and robots in space. And these are the Spheres robots. They're free-floating robots that were on the International Space Station, and looking at ways we can plan for them to move around to avoid collisions, and also do things like inspecting the outside of the space station. That was research I did in my PhD, and the PhD is just kind of like a extra studies at a university where you're doing some research into a particular area. And then I had the opportunity after that to come to JPL to do robotics research here. And so what I'm going to do is step through each of these parts of the mission pipeline, and then I'll go into particular detail in one of the areas, which is more the area that I work in, and this is related to some of the work that you guys are doing first. And so first of all is what we call formulation. This is generating the ideas. So this is kind of like the first few days when you get the challenge from FIRST Robotics, really thinking about all the different ways you might be able to tackle the problem. And literally this is going from back of a napkin. So here's someone sketching how he might do a flyby of Venus to go to Jupiter. But then what the people at JPL develop are different tools to go from these ideas into something that's a bit more detailed so you can see if it makes sense. So these are things like simulating what the space, the pathway through orbits would be to get to Jupiter. It could be doing a very initial design for some type of spacecraft, doing some kind of low fidelity, so some simple analysis of the system, just as a first step to see if it makes sense. And it's all that kind of early ideas which really then sets the path for what we're going to do going forward for a mission. And then we have technology development, and this is what I'll come back to in a bit more details. This is basically doing the research to develop the technology, the widgets, the devices that will enable something we want to do in the future. And so here's some examples, I'll just mute that, of different robotics research that is done throughout JPL. And so these are different mobility systems that we're looking at. On the top left, we have something called the Axle rover that's designed, it's kind of like an abseiling robot to go down very extreme terrain. So steep slopes, down cliffs, over large rocks, to access some places that might be really interesting for the science. So these are some tests in deserts in California. The bottom left is a micro gripper, micro spine gripper, where it's got these very tiny spikes that can grip to surfaces to go up vertical planes, which is very interesting to access, again, those cliff-like areas. On the bottom right is a climbing robot that was climbing up ice, but also can use those same micro grippers to climb up rock walls. And then on the top right, we see a system that's got moving wheels on legs that it can use to move in different types of gaits, we call them. So it could be just driving, it could be stepping, it could be what we call inchworming, so moving a bit like a worm or a caterpillar, to go over this really extreme terrain that we anticipate on other worlds such as Europa. And so researchers, roboticists are designing these robots and going out and designing the algorithms as well, the software, and then testing them on a lot of different extreme terrain to see, okay, how do we do this if we were to send a robot to another world? So just like you guys might design your robots, go out and test it for the task, and you may test it for little subsets of the end competition task to see if it works and then make developments and improve it. So the same kind of thing we're doing here with the goal for looking at applications for exploring other worlds. So we'll come back to a bit more of that technology development, but that's a big part of what JPL does, a lot of engineers working on that. The next part is design. And so this is something that you're probably familiar with. Probably some of you have used some CAD programs, designing different parts that you're going to then manufacture to go on the rover, on your robots. Same type of things done at JPL, designing the different components that's going to go on the Mars rover, for instance. And there's also some interesting aspects that is being used at JPL of using augmented reality to place parts in the real size as they're being designed without being built, so people can collaboratively look at what the design will look like, but also, can I actually build this? Can I put these parts together? If I put these two bits together, can I plug in the wire appropriately? So to kind of get an idea of what it will look like for manufacturing and have a feel for the size of it. Next step is manufacturing, which is probably quite similar to what you guys would have been doing pre-COVID in terms of you're using different tools, different materials to build the different components to make your system. And JPL does a lot of that, but there's also some manufacturing that is outsourced. So another company is paid to build different components. I can show you some examples later on. The final part, well, not the final part, but the next step, which is a really important step for going to space, is verification and validation. And basically this just means testing to make sure that your robot does what it should. And this kind of covers all different types of systems. This is a full Mars rover going through a final mobility test. So this is the actual Mars rover that's on Mars now, the first big Mars rover. And it's in the clean room at JPL, driving over just a bump, and with lots of people watching closely to make sure everything works. And so this is really what we call a full system test. You're testing the wheels, the motors, these mechanisms here, which is called a rocker-bogie system, which is basically like a suspension, as well as the software to drive. So it's testing all those components. But in the lead up to that, each component has been tested individually. So there's been individual sets of tests for each of the motor assemblies, for the suspension mechanism, for the software. And really it's designed because if it doesn't work when it gets on Mars, we can't send someone there to go and fix it. But we also can't test it on Mars before we go because we don't have Mars in our backyard. And so all those tests are basically to make sure that there's no bugs in the software. And this is very similar to what I'm sure you guys go through to be testing and debugging to make sure that your robots are working as intended, to try and find out where there's some bugs, some issues that you can try and test them before you come to the competition to make sure you've resolved them. So that's a big part of which is important for things going to space, but it's also important for everything we're doing with robotics. And I think you guys are probably learning some good lessons on that. So then the next step, once you have this robot on Mars or orbiting a planet or orbiting a moon, is operations. You want to be able to drive it around or command it to do things to get the science that you're looking to get. And so for the Mars rover or Mars rovers, does anyone, this is normally try to like to do this live where I can get some feedback, but the question is how do we drive it? And if people have some thoughts and come back to it at the end of how you might like to drive it. But one of the challenges with Mars is that there's a long time delay. It's about, can be around 8 minutes to go there and back. And so if any of you have played video games and you're online with some friends and you have some lag because you've got a bad connection, even like 1 or 2 seconds of lag is really frustrating, right? You kind of feel like you can't control it properly. imagine 8 minutes of lag. So we don't control these with Xbox controllers or PlayStation controllers. You're not actually driving it in that way. However, there are people whose job is the Mars rover driver. And so it's a pretty cool job title, but what do they do if they're not actually driving it around with a joystick? What they do is they do drive rover planning days. And so they'll get the images down from orbit, such as these images you see here. These are 2 stereo images, so we can get depth by comparing them together. And that allows us to assess the terrain around the robot. And then from that, to plan out how we want to drive the robot to go to wherever our goal is, but also to do that safely. And to do that, we use simulators to help us out. And I'm not sure, there may be some simulators that you'll be using for the next competition, but those simulators will help us to say, okay, we're going to drive forward and turn a circle and face the camera in these directions. And then we simulate it to see, okay, is the rover able to do that? Is that going to be safe? And we're simulating that on a terrain map that comes from the rover's sensors. And then once the team's happy with how that's done, they send up a full sequence of commands. So a set of instructions that go to the rover so it can execute that on the next day. And that repeats day on day. And finally, the whole goal of every mission at JPL is the science. And so everything that is done for this robot is to get information from different sensors that can be sent back to Earth. And then there's different ways of processing that information to learn more about geology, to learn more about different aspects of Martian conditions. Depends on obviously what the mission is. And so just like in FIRST, you may score points by doing a particular task, be it going up on the platform, putting the spheres into the different locations. Obviously it changes each year. At JPL, we score points by getting good information to scientists so they can learn more about the universe. And so that's kind of really the goal of everything that we do. So that's a very quick overview of, I guess, my summary of what that mission pipeline is for robots at JPL, at NASA. And again, I think there's a lot of similarities to the pipeline that you guys go through for developing robots and for other robots on Earth as well. But what I wanted to go through is a little bit more detail on technology development and another kind of close similarity to what you'd be doing at FIRST. And so one of the things that really we're doing here as we're doing research and development is we're constantly improving what we can do. We're constantly improving our designs, our capabilities, until it gets to the point that we're confident that we could send something to another planet and for it to work. And so that's kind of similar to what you guys would follow through in your various years. Obviously, you had some great results recently, but you started off with an initial design. You had prototypes that would develop it into a more advanced design, and you continue to iterate and improve year to year, but also, I'm sure, within a year. As you learn different things, you test it, you realize there's issues, and you look to improve. So that exact same process is what we do at JPL. And I'm going to give you an interesting example for that. This is some research that I was involved with. This is a quadrator, autonomous quadrator, that is a result from a lot of research and development. It's trying to be a very compact quadrator that can be very capable and autonomous. So it has 2 cameras, and those 2 cameras track what we call visual features in the environment that we've already mapped. So in this case, we already know the environment around us. It uses that camera to work out where it is. We also give it a 3D map and tell it where to fly around this 3D map, and then send it to the drone, and it goes and tries to fly that as accurately and quickly as possible. And this is just a warehouse at JPL where we're trying to test that out. We thought we'd test it against a human in this case, just to see what our capabilities are. This is our drone that's flying around, we thought, relatively quickly and smoothly. Although the human doing some practice runs was also quite quick. And we did a time trial where we each ran around the same course and saw how quickly each of them could go. And we thought we did quite well with the autonomous system, but it was quite capable. However, the human learnt a lot, and so they quickly got better and better, and in the end beat us. But really the goal here is developing the technology that we could use in future missions. And so here is an example of the vision system. So you can see the cameras here, what the cameras see. And with those those images, it's tracking features to match the environment and really accurately track where it is, which is important for flying where we want it to fly. And so when we test that, we want to see how reliably does it know where it is so it can fly where we want it to go, but also fly without crashing. And so here we are, it doesn't know necessarily that the door's there. We've just told it to fly back and forth through the location that is the middle of the door many times in a row. And so if it was to know where it is accurately, it would fly through fine and not crash. If it was to not be able to know where it is, then it would crash into the door. And so we're able to show that it was able to reliably fly there and accurately know its position. And all of this on quite a small system. And so you see the size of it here. It's quite small. And it has quite a lot of capability inside it. And part of that's because of the hardware, the processors on board. And while this is flying on Earth, it's not necessarily something that we're going to send to space. Some of the technology designed within it has been transferred to some very exciting projects. One of the things we're interested in is potentially flying on Mars. So this is the 25-foot vacuum chamber at JPL, and this is how we can simulate as close to Mars as possible. Now, there's two things that you guys can probably know. Maybe you can try that in the comments of what makes it difficult, or what are the factors that are different on Mars that's relevant for trying to fly. Not sure if I can see comments as they come up, but maybe someone can note that there. Gravity, different gravity, yep, spot on. So gravity, is it less or more on Mars? I can see the comments now, so feel free to jump in. Less, okay, so that's gonna make it easier, right? It's about 1/3 of what it is on Earth. So that's gonna make it easier. What else might be different for flying on Mars? Air, yep. What's different about the air? Climate, atmosphere, yep, spot on. And pressure. So there's less air and the pressure is lower. And so the density is lower, that's right. And so the air density is about 10% of what it is on Earth. It's mostly carbon dioxide. What, do you guys think that makes it easier or harder to fly? Harder, spot on Nathan and Suvan. Exactly. So air is not as dense, so it makes it harder to fly, but gravity is less. What do you think the balance is? Do you think it's easier or harder overall, combining those two things? It's a tough question because they're kind of both going different directions, right? Harder overall, that's a good guess. That's kind of my guess as well. And I think generally it's a lot harder. And I also saw wind there, Trump. That's a good point as well. We can get back to that if you want to ask a question a little bit later on. So here it is inside the vacuum chamber. So this is not worrying about weight at the moment. This is just looking at, can we produce lift in Martian type air? And so the vacuum chamber pumps out so there's no air and then puts in CO2 until it matches Martian conditions. And here they're increasing thrust and it slowly takes off. Let's just go back here. So you can see we're able to produce lift. So that's great, which means we spin the right rotor design fast enough, we can actually produce enough force to move something up, even in the low density air. And so, okay, we just need to make a system that can do that. Now this is testing a very kind of just prototype system. It's quite small there to try and simulate similar gravity by making it very lightweight. And it's again in the vacuum chamber, pumped down to be the same as Martian air. And trying to fly to see, okay, can we control it if it's going to fly? So as it takes off, it's not being controlled very well. It keeps bouncing around. And that was a lesson learned by the team. This is an early prototype that actually it's kind of, we can produce lift, but it's kind of hard to properly fly in Martian conditions. Now, can anyone guess why that might be? So we could produce enough lift to get off in the air, so that was fine, but we couldn't control ourselves to just hover. Anyone guess why that might be? But it's a hard question.
The atmosphere?
The atmosphere, yeah, it's definitely something to do with that for sure, yeah. What do you think about it?
You're saying that it's dense or something?
That's right. So Oh, sorry, was someone trying to say something there?
The gravity might also make it a little bit difficult. You have less weight to sort of damp your motion in any particular direction.
Yeah, that's a really great point. And it's a really a combination of those things where it is the kind of the damping is the right question. And it's kind of the controllability that gives you is really important. And to give an example is imagine you're in a pool, a swimming pool, and you move your arm up and down. You're going to feel kind of a lot of resistance to your movement, right? And let's say you can just float in a pool, right? You don't have to do anything, and you're kind of stable. You're not going to move around too much because there's a lot of density in that pool. Now, if you do the same thing in air, you move your hand around in air, you're not going to be feeling that same controllability, that same stabilizing force that you would feel in water, because the water is a lot more dense than air. And now Mars is kind of the same thing again, that you go from the air we have on Earth to Martian air, and the density is a lot less, so you have that less support, that less stabilizing force, and so you have to really do it all yourself. Whereas on Earth we have the air, which is actually quite dense. So if you move your arm, you can kind of feel the air moving across your arm. You wouldn't be and hover in one position, showing controlled flight. And so with changes to the control, they're able to successfully do it and show that we can actually have a helicopter flying stably on Mars, which is exciting and the result of a lot of developments. But now the software and the hardware to do that on board, a lot of that actually comes from that first flying project I showed you with that small drone flying around a warehouse. Very similar hardware and integration has gone into enabling this to be possible on a helicopter that is lightweight enough to be sent through space, but also has enough of the capability to fly and to be able to track its position as it flies. So that's very exciting. This is a prototype being tested, and this is actually the flight model, the helicopter that's going to Mars. A very simple test because they're being more conservative with it, but just taking off from a platform and showing that the flight model can hover and fly. It's about to take off now, I think. There we go, just a very short takeoff and hover. And there it is flying reliably. And as you may have seen, it is currently on its way to Mars. What will happen is that the next Mars rover, Perseverance, will drop off Ingenuity, the Mars helicopter, drive away a safe distance, and so it can observe what's going to happen without being at risk if something was to go wrong. And then the helicopter, sometime early next year, will start off for the first powered flight on another planet. It has large rotor to spin up fast enough. And just like that research project I was showing you that I was involved in, it's using visual cameras to track how it's moving. And it's looking at the ground, looking down at the ground with the cameras that you see there. And it uses those images to help track how it's moving so it can stay in the same position or fly where it's commanded. And the idea of this is that it's a technology demonstration. It's designed to demonstrate that we can fly on Mars, so we could use that to potentially have a bigger helicopter that can carry different science instruments. And so it's all very exciting. And again, it's part of that prototyping process that I was describing before. I might stop there if there's any quick questions, and I wanted to get on to some other details relevant to the Mars helicopter. But are there any questions now on the Mars helicopter?
So when you test the Mars helicopter, you use like a string to basically get rid of some of the weight.
Exactly.
How do you make sure that the string is like vertical at all points? Because if the tension is horizontal or like, angled or something, that could potentially lead to some different accelerations that are not quite exactly g/3.
Excellent question. And actually, there was a lot of engineers at JPL spending a lot of time trying to solve that exact question. It's a really difficult thing. It thinks like, okay, just hold it up by a string. But the design of this is such that it's hard to simulate it properly. Like, you're right, if the helicopter was to swing over here to the side, then the cable would be pulling up at an angle, and so the dynamics would not be quite the same, and the gravity offload would not be the same. It's only really valid when it's going straight up and down. How do we mitigate that? Say we, this is my colleagues working on this, not necessarily myself. Part of it is you see with this camera view that it's quite a tall chamber. And so if you're thinking about your geometry of your triangles, if you think of can I draw it?
So small angles, you're generating small angles.
Yeah, so like if you think of your triangle here, it's a very bad triangle. But let's say we were to go out to this side, and if your helicopter was around here, then you're having some more force that's going to pull to this side, right? However, if you increase this distance, where are we going? Then that angle is going to decrease. Does that make sense? So
yeah.
This triangle, as opposed to this triangle, is going to have kind of different components or different percentage of the force is going to be going across in this direction.
Okay.
And so really we're trying to raise that pulley up here as high as possible is basically the approach taken, and just flying up and down.
Okay.
Yeah, kind of trying to stay in the middle. That's a really good question.
All right, thank you.
Any other questions on that?
Yes, Ben, how far of a distance is the helicopter going to travel once it's in Mars? I mean, I understand that it's going to have several lifts or several missions, reconnaissance missions. I guess, how high would it go and how much would it travel?
Yeah, good questions. And it's kind of a test plan of incremental flights. So we kind of go to the animation. Where are we going here? Okay. So the first flight is really take off and land. Something very simple. We want to kind of gradually increase the risk because, again, we can't fix it if anything goes wrong. Right. So it's first of all, let's just take off and land, and let's take off and move left, then right, then land. Let's take off and then do a small little box and then land. And that's going maybe 50 meters high and maybe moving about 10, 20 meters. Then if that's all successful, then there's a set of about 3 to 4 flights that are planned to take some more challenging, attempt more challenging trajectories, let's say trajectory being where it's going to fly. And so that may be flying out to take a picture of something in particular, going maybe a few hundred meters. It may be going and flying closer to a certain feature, or it may be just trying to see how far it can fly, to see if it can just go as long as possible to get that data back to really learn more about it. Because again, it's for technology development. So those additional test flights will be to learn more about the technology. And so it may be fly as fast as possible so we can see kind of how the charge of the batteries affect the flight time. Its flight time is probably about 8 minutes or so, I think. So it's not very long. It being solar powered, it has to wait and then charge up its batteries to go again. But I think it's the nominal ones are probably on the order of 10 to 100 meters per flight. So something not too large, but then those later ones may be longer to really stress the capability.
Another question, sorry. You mentioned recharging. It uses solar panels to recharge. What's the time scale for recharging, and where does it have to be to recharge? Does it go back to the rover, inside the rover, or will the helicopter be outside and try to recharge?
Yeah, great question. So these are the solar panels you see on top. They're pretty basic. They also serve as antennas to communicate back to the rover. And those solar panels are the primary means of charging. So once the rover drops it off, there's no more contact with the rover in terms of no physical contact, still communicating data. And so then it's all based on the solar panels. But the solar panels don't charge that quickly. They're not, you can see that area is not quite that large. And so basically it just has to wait for a while to charge. So basically 1 day of charging is kind of what it needs, or one day. It's its day of operation is very much majority charging, let's say. So it has its test flight, it comes back and land, and then it's just charging for the rest of the day. And so really kind of majority of the day is just spent charging the batteries and keeping itself warm at night, and then having enough charge to go and do the test flight. Because it's quite difficult to have enough battery power in quite a small system with just being solar powered. So that's kind of how it works, but it basically means that it's most of the time charging, but it's not really doing that much else when it's not flying anyway. And so where does it have to be? Just somewhere with enough sunlight, but the target area is not going to be near many things to obstruct sunlight anyway.
Okay, thank you.
So we can keep doing more questions. What I'll do is I'll quickly show this, which is how the helicopter is going to come off from the belly of the Mars rover. So this is kind of a plate that is the belly of the Mars rover, and this is a shell that's protecting the helicopter once it lands. So first of all, the shell is removed, and then the rover will drive forward away from the shell. Then this latch releases the helicopter there, and then there's a movement to slowly lower it down. You can see it's in a position where its two legs are held up above it. So it's initially on the side and it comes up so it's facing the right way around. And then there's a deployment there to drop down the legs. These are all explosive bolts. Oops, sorry. And so it drops down the legs. They're on just elastic hinges over here. And then eventually there's a bolt to just drop it off and drop it down the surface, and then the rover will drive away. So that's the deployment, which just kind of seemed a little bit crazy. And this is kind of some of the activities I can play in the background when there's questions that are involved in actually putting the helicopter onto the plate that will go on the belly of the rover. This is the actual flight model getting assembled. I can just leave that in the background. Are there any questions on the Mars rover? Actually, it's a good close-up. You can see the rotor blades are carbon fiber. They're very specially designed.
How much does it weigh?
Good question, actually. I don't know the exact number. I'd say it's a few kilograms there.
A few kilograms.
It's fairly light, but just the weight of the components needs to be roughly that weight. And sorry, that's in metric units that we normally use at JPL. So it's in a position where it's ready to be deployed, and this is the plate where it will drop off from. And this room is the clean room at JPL, so they're all wearing what we call bunny suits, which are to keep any of particles and stuff from our people to be going off onto these spacecraft to keep them clean, so there's nothing that may cause a short or anything like that. But also there's a need to keep it clean. We don't want to send any of our biology to Mars to potentially impact any potential biology that may be on Mars already.
Right.
Any other questions from the team on the Mars helicopter?
Not really.
Cool. Okay. And so to say, okay, let's go in the belly of the rover there. Slowly being lowered down. So you can see that's kind of where it goes here on the belly of the rover. And so that's kind of the path of technology development. And you remember, if you kind of remember what I was saying before, we go from research on helicopters doing racing around a warehouse, which is also beneficial for Earth applications, but some of the vision navigation and the compact hardware then goes into those lessons go into the Mars helicopter. We do different tests and prototypes of the Mars helicopter that we learn lessons from, and we design new versions of it. And then we eventually get up to a system that we can test and do all the tests that we think are necessary to convince ourselves it's going to work on Mars, and then it can make it onto the Mars rover and be on its way to Mars. That's the same process that you guys go through for developing your robots and your systems for FIRST. It's just a kind of at a different topic and a different scale with more people. So hopefully kind of you can see the relevance there of what you guys do in FIRST to what JPL does for robotics, but also what robotics research and development is in general. And I have another example to go through that's slightly different, but can show you some of similar ideas on the same thing. So I think you had someone talk to you about this before. Might have been Carlin was talking to you about the subterranean challenge. Did you guys hear about that?
A little bit. Yes, yes, actually, we have.
So I'll touch a little bit on it. This is an area project where I'm working on a lot. And this is really developing technologies to be able to go and explore caves. We see caves on the moon and on Mars. And they're interesting places for understanding the geology, but also potential human habitation, and interesting places for looking for potential evidence of past biology on Mars, for instance. And so this challenge is really about search and rescue, though, in underground environments. So you have to be sending in a team of robots to autonomously go up to 8 kilometers in a short space of time and to find objects that we want to detect and report their location back to the surface. And there's no GPS because we're underground. And so essentially, this is what we want to do. We want to be sending these robots. We're going to go autonomously explore some cave environment, send multiple robots out because there's a large cave to go and explore. As they go through that environment, we want to send it back to a base station where it reports a map and the location and status for all the robots, as well as locations of interest. So reporting objects that we may want to go and inspect in the search and rescue. There may be people that we want to go and save, or places we want to send people. Or in a science context, it may be areas that we want to send back more data about that may have interesting science observations. So this is a movie, this isn't reality, but that's what we're aiming for, something like that. And we're doing that in the competition with these robots. There is a wheeled robot we call Huskies with a sets of LiDARs on top and a lot of computers. And this Boston Dynamics robot with a lot of our computers and sensors on top called Spot. So this is our team of robots that we've been testing in the DARPA Subterranean Challenge. And most recently, we've been trying to test these robots for exploring caves. And in particular, something that's called lava tubes. These are caves that have formed from lava flow from volcanoes. And there's some great lava tubes in a place called Lava Beds National Monument in Northern California. And so this is what we see here. So this is, Nebula is kind of our name for our development of autonomy. What we have is we have Spot exploring the surface, looking for the opening to a cave. As that finds that, it goes down into the cave. Descending over some rough terrain, and it's kind of trying to be very stable on its footing. And then it goes from the entrance through to what we call the twilight zone and into the midnight zone of the cave. As it gets further away from the light from the entrance. In this case, we were looking for different objects, for drills, but we could be looking for scientific locations of interest. Has to traverse over quite rough and steep terrain and still stay stable. You see some very extreme terrain here with the lava flows. It's just hard for people to walk over. It's navigating around different passageways to find the best way to explore through. And even for very large vertical changes, if it can find a sufficiently, I guess, a smooth enough path or a safe enough path, then it can find its way down. And looking at locations of interest, such as different places there could be some scientific novelty, so things that stand out as different, or could be some type of biology. And again, we've placed objects there as kind of salient test cases. And then there's some narrow passageways it has to go through, some large open spaces with no lighting except for what it carries. And again, just looking for different objects in the environment. This is just a very simple example of having a particular object. There's boulders it might have to step down, quite large obstructions, low ceilings it has to duck down through these cave environments. As it goes, it's producing a map. This is a LiDAR-based map that it produces as it explores, that it can use to localize where it is, localize observations it makes, and then to also have information on what the cave topology looks like for for the scientists. Eventually, we want to get it back to the surface so that it could send this information back to Earth. So as it's returning back, it goes up the same types of terrains, navigating its way where it can be safe. And makes its way back to the surface. This is all something that we're developing it to be done autonomously. So there's just one command sent from the surface to go explore that cave and come back and report your findings. And it's supposed to plan, navigate its way, and then eventually work its way back out and send that information back to either a lander or back to the surface. And so that's the ongoing work that we've been doing, and so this is some recent tests that we've had to demonstrate that capability. A lot of the JPL work is in the autonomy, whereas the legged mobility, the robot moving, that's from Boston Dynamics, the company that makes the robot. Whereas JPL is, and our team, which you can see here, they are developing the brains of it, the smarts of where to go, how to produce that map, how to look for objects of interest, how to decide when to come back, and eventually coordinate with multiple robots as well. And again,
I'm sorry.
Go.
That part of Nebula?
That's right. So Nebula is our autonomy framework that we're developing, which you see kind of at the start here, which is kind of encompassing a lot of the algorithms that are describing the robotic planner, the robotic localization and mapping, detecting artifacts, all those different things that are going into the autonomous system.
Yeah, we had actually our very first guest speaker was talked about CoStar, and she was a member of the CoStar team. Her name is Carlin Lee.
Yeah, and Carlin was doing some great work on the communication side as well, of how if we send in multiple robots, how they communicate with each other to send the information back to the surface.
Yes.
So it's a really big effort by the team in a lot of different areas that are beneficial both to Earth applications for search and rescue, but also developing what we think is important for exploring caves on the Moon and Mars.
What was your part of your work for CoStar? I don't know. Were you designing the type of robot like you're showing there? Or was it more information on how, like, in the systems point of view versus the mechanical robot?
So my work's mainly on the software side of things, and I'm responsible for I guess the biggest part is the localization and mapping, which is what you see here. So using the LiDAR on board to track its position and produce a map of what's around it. So we call that SLAM, simultaneous localization and mapping. And that's the primary thing that I'm looking at, as well as detecting objects of interest and reporting their locations. And looking at the software, as well as a little bit of this hardware in terms of the choice of which sensors we want, to be able to then get the capability that we want from the robot.
What type of sensors did you guys choose?
So you can see some of the sensors here. So look at the spot. We have the Velodyne LiDAR. It's quite expensive, but it's a LiDAR which provides really valuable depth information. So we get range from 16 beams that spin around the robot. There's a thermal camera on the front, which is for detecting objects of interest. So for instance, if we're looking for a survivor in a search and rescue context, the survivor should show up in the thermal camera. That's just a protective shell around the camera. We have 3 Intel RealSense cameras, which you see here. These are both visual cameras as well as depth cameras that we use for detecting objects of interest. There's a gas sensor here, which we're trying to detect high concentrations of CO2, which may indicate people being around. And inside there's some inertial measurement units, which are IMUs, which can detect how the robot moves around. Additionally, I mean, you can see on this robot, there's 3 LiDARs. Whereas Spot has lots of these depth cameras. You can see some internally on the body. The wheeled robot has what we call wheel encoders. So we get from the rotation of the wheels an estimate of how it's moving. That might be similar to what you guys are using.
Yes.
It's a great source of information.
Encoders.
And even though these guys don't have wheels, they have similar information. They can track the forces and the dynamics of the robot moving to infer motion from how it's stepping. So we call that kinematic odometry. And that's what we get from the Spot robots, which is similar to the wheel odometry, but just for these legged systems. Oh, sorry. Cool. So I think that's kind of the summary of what I wanted to go through there. I'm happy to answer any more questions about each of these areas, and I can go into more detail and other things up as needed, but I just wanted to make sure I gave plenty of time for any additional questions on the Mars helicopter, on how we do robotics at JPL, on the DARPA Subterranean Challenge, on Spot, whatever you guys would like to ask about.
Don't be shy. I have a question. You mentioned AR technology, or is it AI technology, when you were doing prototypes and doing test runs of the helicopter, and how you were designing, I don't know if there were props or terrain. There was a picture where a couple of people were standing, and I think there was some kind of obstacles or what have you. How much did AI contributed to your designs?
So this is for the drone project, you mean?
Yes, for the drone.
Sure. Yeah, let me get the shared screen up. And I saw there's a few questions in the chat. I'll get to after that as well. So in this case, the video said AI, but it's actually not AI at all. It's just kind of algorithms that we would develop there. So there's no machine learning or data-driven stuff. There's no neural networks. In this case, this was an early stage where we were using prior knowledge of the environment. So we would walk around beforehand. Let's just try to get it here. Okay, so you see here is a 3D mesh of the environment. So this is a 3D model of the environment that we're in that we did just before we ran. And so on the base station, we would then plan with some trajectory optimization algorithms how to fly through that environment, avoiding obstacles. We'd have a representation of the obstacles there that we'd have to avoid. And so as we plan, we'd see in 3D space, okay, we need to keep at least this distance from any obstacle. And then the assumption there is that when flying, the robot will be able to keep close enough to these lines, these trajectories, to be able to avoid collisions. And so in that case, we were using that prior knowledge of the environment to be able to ensure that we wouldn't collide.
Cool, thank you.
No questions. So I saw Suvan asked, how was it stabilized again? I'm guessing that's in reference to the Mars helicopter. So basically it was in control. So because we don't have the damping, we need to have a much more active controller that is able to adjust and stabilize itself. And so if you're kind of swaying around, no, that's all right, Savannah, just because I didn't get to it until now. As you're swaying around, then so again, like let's say I'm moving side to side and I'm trying to stabilize myself to the middle. If I'm in water, it's going to kind of stabilize myself. Whereas if I'm in air, I'm using the control of my legs a bit more actively to hold myself steady. So it was a higher rate controller on the helicopter that would allow it to stabilize. So just kind of more, that's both in the mechanisms for control as well as the algorithm to control it. How many failed attempts did it take to get the desired result, Tron? Good question. I don't actually know. I would say that prototype test that you saw, they ran a few of those, and that was a kind of a big result that it's really hard. Then instead of, I think they maybe gone through a few iterations after that, but I think that test gave them a lot of information to really understand the problems. And they would have done some smaller scale tests of different components to get iterations on smaller scale tests before they went to that full prototype. But I think, in terms of count of prototypes before they got one working, it would have been in the order of like 4 or 5 full prototypes with a lot of smaller test cases as well. But I don't know the exact number. That's just kind of my impression from the process. How do I teach the AI to function in Mars climates when testing on Earth? Yeah, great question, Hannah. That's really hard. I can stop sharing. So basically, we don't know what it is. We don't have full Martian conditions yet, and we can't reproduce it all, or it'd be very, very expensive to reproduce it all. Sometimes we reproduce different components of Mars conditions. So it might be producing the same atmosphere by pumping in CO2, having the gravity offload to simulate the gravity. Sometimes for Mars rovers, we might try to have very similar gravel, some similar what we call regolith or soil for the rover to drive over. But it's very hard to have all those things together in the one test. And so that's just a general challenge with this line of developing robots, is that we just can't test where we're going to go and deploy it. If you can, definitely do it, but in this case we can't. And so it's really just testing as each kind of thing that we think is going to be challenging and making sure the system's robust to each of those conditions. And what we do is we design a set of tests, and some of those tests may be in similar Martian conditions, some of them may just be in Earth conditions. But a set of tests that we think through the design, as we're designing, that if it passed, so the helicopter or the rover, if it passed our set of tests, then we're confident that it's going to work on Mars. We can't be 100% sure, but we can just be as sure as we'd like to be. Still, there may be some condition on Mars that it's got the different temperatures, maybe there's some wind coming through, maybe the atmosphere is less dense that day because of the different solar conditions, and maybe there's some dust conditions that we weren't able to combine them all together and it makes something that's very challenging. There's a risk that might happen, but from what we know of Mars, I think that risk is small enough from the different tests that we have. And I'll just jump back to Trung, you were mentioning wind again as well. Wind is something that, because the atmosphere is less dense, then the wind is not going to have as much force, if that makes sense. So if you have a waterfall coming at you, it's going to be very dense, it's going to have a lot of force. If you have wind, it's not as much force. And again, if you have less dense wind, it's less force. However, it still can be there and it still could be an impact. And that's one of those things that we don't know all the cases that could happen. We think for most cases, the helicopter is robust to that. If wind does come through one time, we can just wait. But also so there may be some corner cases which is difficult, but in general, we think the helicopter is robust to that type of wind. Even though it is less force than what it would be on Earth, it could still cause an impact. Some great questions, guys. Thanks.
Great. Well, if we have no more questions, I just want to thank you so much for giving this talk, and it was very informative. I learned something, and it was also exciting at the same time. Great, cool. Again, thanks for the opportunity. Good luck, everyone, for First Robotics going forward. And I guess congrats all for diving onto the team. I think it's a great experience being involved in First, and from my experience, I wasn't involved myself. I was involved in some other competitions, but the experiences you guys get in First set you up incredibly for careers in STEM in general going forward. And so I've seen that through a lot of my colleagues, and people who've had experience in First really understand how to make things work in the world. So dive into it, guys. It's a great opportunity, and really congratulations for pushing through in these trying times and getting involved in something so cool. Thank you. Yeah, we'll keep you posted when we first start in January. Just keep you, I guess this is a heads up just to let you know. We may ask for advice or something like that. But sure. Anyway. Definitely. Yeah. Looking forward to hearing about it. Thanks. Great. See you guys.